In this videotape, we're going to discuss properties of logarithms. I'd like to start by going over with you the basic definition of a logarithm. If y is equal to the log of x to the base b, y is the logarithm of x to the base b, then y is the power that you'd have to raise b to get x. In other words, a logarithm is a type of exponent, a type of power. We discussed this in the last videotape. And if y is equal to the log of x to the base b, then y is the power that you'd have to raise b to get x. Now here we're assuming that b, the base, is a positive number, but not equal to 1. If it were equal to 1, we would have some trouble here because 1 to any power is 1. Okay? So we would not be able to get the x values that we want here. Now, one thing I want to point out is that x, because of this, x is implied to be positive. In other words, the argument of the log function, it's the log of x. X has to be positive because x is b to the y and b is positive. Okay? It doesn't matter if y is positive or negative. For example, if b were equal to 2. Okay? Obviously, 2 to a positive power, for example, 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Certainly, if you're raising 2 to a positive power, the result is going to be positive. On the other hand, if you raise 2 to a negative power, 2 to the minus 1, that's 1 over 2 to the 1, or 1/2. 2 to the minus 2 is 1 over 2 squared, or 1/4. So as long as b is positive here, doesn't matter if y is positive or negative, okay, x is going to come out positive. Of course, if y is 0, b to the 0 is 1. So x will be positive. Okay, now I'd like to list for you certain properties of logarithms. All of these we could prove. I don't want to take the time here. Okay, and they're probably proven for you in your textbooks. What I would like you to do is to understand these basic properties and be able to use them. Now, we have them over here, properties of logarithms, and I'll give you time to copy them down. In what follows, x, y, and b are positive real numbers. b, which represents the base, is not equal to 1, and r represents any real number. The first of these says the log of 1 to any base is 0. Well, this is trivial to prove because it comes straight from the definition of the logarithm function. The log of 1 to the base b is 0, since 0 is the power that you'd have to raise b to get 1, or b to the 0 is equal to 1. The others are not that obvious, okay, but they can be proven without too much difficulty. In 2, we say that the log of x times y to the base b is the log of x to the base b plus the log of y to the base b. That is, the log of a product, okay, to the base b is equal to sum of the logs of the factors to the base b. I don't have to specify each time to the base b. In these problems, we're assuming all the logs are, say, logs to the base b. So the log of 1 is 0. That's no matter what the base is. The log of 1 to any base is 0. The log of a product is equal to the sum of the logs of the factors. Okay? In 3, I'm telling you that the log of a quotient is the log of the numerator minus the log of the denominator. The log of a fraction is the log of the top minus the log of the bottom. Remember, x and y are positive numbers here, so there's no difficulty. You don't have to worry about division by 0, nor do you have to worry that the argument is not positive. X and y are positive numbers. The log of a product is the sum of the logs of the factors. The log of a quotient is the log of the numerator minus the log of the denominator. The log of the top minus the log of the bottom. And finally, the log of x to the rth power, okay, is r times the log of x. That is, you may bring the power down in front as a coefficient. The log of x to the rth power, okay, it is x that is being raised to the rth power. It's not log of x quantity to the rth power. It's the log of, in a sense, the log of x to the r. The log of x to the r is equal to r times the log of x. Okay, so copy these down. These are the basic properties of logarithms, and we're going to be using them in a few moments in some examples. Once again, the log of 1 okay, is 0. The log of a product is equal to the sum of the logs of the factors. The log of a fraction is the log of the top minus the log of the bottom. And the log of x to the rth power, you can bring the r down in front and make it r log x. And these are going to be helpful to us. By the way, those of you who've never studied logarithms before may feel that you've seen something like this, if not quite this, something related to this. You may be thinking about the rules for working with exponents. Let me list the rules for working with exponents down on this board here. And you'll see certain relationships. Okay? Properties of exponents. Exponents were discussed in earlier videotapes, but it's valuable at this point to look at certain relationships. Each one of these log statements has a sort of corresponding relationship in exponents. The first one is obvious. The log of 1 to the base b is 0, since 0 is the power that you'd have to raise b to get 1. The other ones are not that obvious. Remember when we were working back with exponents and we're multiplying and we had the same base? B to the x times b to the y. When you're multiplying, okay, two expressions that have the same base, you keep the base and you add the powers. B to the x times b to the y is b to the x plus y. When you multiply, you have like bases, then you add the powers. Now this is not, of course, the same as this, but there is some relationship. It was, in a sense, the first time we went from a kind of multiplication to a kind of addition, which is what we're doing here. The log of a product is equal to the sum of the logs of the factors. Okay, and here we have that when you multiply, and they have the same base, you add the powers. This is not too surprising since there is a certain relationship between exponential functions and log functions. We saw that in the last videotape. And of course, from the very basic definition, the log is a kind of exponent. Okay. This, in a sense, is related to the fact, this third one is related to the fact that b to the x over b to the y, when you divide and you have the same base, you keep the base and you subtract the powers. B to the x over b to the y is b to the x minus y. Now this you've seen before. These are the common rules for working with exponents. And you see, in a certain sense, the basic ideas from the logs coming up. And this last one is a little harder to see. B to the x power raised to the r power would be b to the rx power. For example, if you had like x squared cubed, it's x to the 2 times 3 or x to the 6th power. And this is also a common property of exponents. And it's somewhat related to what we have over here. There are properties of exponents that go in line with the properties of logarithms that we have. Okay, now what I'd like to do is work out some examples for you using the properties of logs. First of all, I would like to expand the expression log of 2x over y to the base 4. Okay? The log of 2x over y to the base 4. Using the third property, the log of a fraction is the log of the numerator minus the log of the denominator. So we could write this as the log of 2x minus the log of y, both taken to the base 4. The log of 2x to the base 4 minus the log of y to the base 4, using property 3. The log of a fraction is the log of the top minus the log of the bottom. Now you could use property 2, which says the log of a product is the sum of the logs of the factors. So the log of 2x is the log of 2 plus the log of x, both in this case to the base 4, minus the log of y to the base 4. Okay, and there you've expanded this. By the way, this particular value can be simplified somewhat. The other two you can't do much with. I mean, the log of x to the base 4 minus the log of y to the base 4. The log of 2 to the base 4 we can figure out. Let's work on that. We know that if y is the log of x to the base b, that means x is b to the y. The log is a power that you'd have to raise the base to get the number. We're interested in figuring out what the log of 2 to the base 4 is. Let's say that's y. Then, if the log of 2 to the base 4 is y, we could write that 2 is b to the y power. In other words, x is b to the y power. 2 is 4 to the y power. We are looking for the power. Y is the power that you would have to raise 4 to get 2. 2 is equal to, now, to work this out, to solve this, we try to get the same base. So 4 is really 2 squared. 2 squared y, so we have 2 is equal to 2 to the 2y. Using properties of exponents, you just multiply the powers. So 2 to the 1 is equal to 2 to the 2y, and if these two quantities are equal and they have the same base, then 2y must be equal to 1. The powers must be equal. Y must be equal to 1/2. In other words, the power that you would have to raise 4 to get 2 would be 1/2, because 2 is the square root of 4. In other words, 4 to the 1/2 power would be the square root of 4 would be 2. So if you want to, you could write this as 1/2 plus the log of x to the base 4 minus the log of y to the base 4. Okay. Over here, we just used the fact that the log of a fraction was the log of a top minus the log of a bottom. Here, the log of a product is the sum of the logs of the factors. We were really finished here, and then we just tried to figure out if we could simplify this a little. And it turned out we didn't need any table. This was something that we could figure out in our heads. We were looking to figure out the power that you'd have to raise 4 to get 2, and the answer was just 1/2. Okay, I'd like to expand the following expression. The log to the base 2 of x cubed, the square root of y, over z squared. The log of x cubed, the square root of y, over z squared, the base 2. First thing I'm going to do, the log of the numerator minus the log of the denominator. Okay, now the first of these is in fact also a product, so you could say the log of the product is the log of the first factor, which is x cubed, plus the log of the second factor, which is the square root of y, which I'm going to write as y to the 1/2 power, minus the log of z squared, all to the base 2. So the log of x cubed plus the log of the square root of y, or y to the 1/2 power, minus the log of z squared. That was using, from here to here, I used property 3, and from here to here, I used property 2. Now, finally, I'm going to use property 4, which says if you have a log of something to a power, you can bring the power down in front. And instead of the log of x cubed, I'm going to make it 3 times the log of x to the base 2. And then here, 1/2 the log of y to the base 2 minus 2 times the log of z to the base 2. Sometimes it's helpful to be able to go the other way. So instead of expanding an expression, I'm going to give you an expanded expression. I'm going to want you to write it as a single logarithm. Okay, so write as a single logarithm, 2 times the log of x to the base 3 plus 3 times the log of y to the base 3 minus 1/2 the log of z to the base 3. I'm going to use the properties of logarithms in reverse this time. Okay, first thing I'm going to do is to make use of the last property. If we have 2 log x, that must be the log of x squared. If we have 3 log y, that must be the log of y cubed, so on. So we can write this as the log of x squared to the base 3 plus the log of y cubed to the base 3 minus the log of z to the 1/2 to the base 3. Now, I'm going to use property 2 in reverse. We have the log of this plus the log of that. We have the sum of the logs of these two things. We can make it the log, because they have the same base, the log of the product, the log of x squared times y cubed. This would be the log of x squared plus the log of y cubed. The log of a product is equal to the sum of the logs of the factors minus the log of z to the 1/2, of course, is the square root of z. Okay? And now finally, I'm going to make use of property 3. The log of a fraction is the log of the top minus the log of the bottom. So here we have sort of like the log of the top minus the log of the bottom. I'm going to rewrite it as the log of this fraction. So we get the log of x squared y cubed over the square root of z. It would be the log of the top minus the log of the bottom. This breaks into the sum of the logs of the factors. The powers go down in front, and we're back where we started. So we've written this as a single logarithm. Okay, now I would like to do one last example with you. And in this one, I would like to actually solve an equation involving logarithms. I want to solve for x log of x plus 6 to the base 3 plus the log of x to the base 3 is equal to 3. We want to solve for x. Now the trick here is to get left, say, in terms of a single logarithm, and then to make use of the definition of logs to switch this from an equation involving logs to one involving exponents, which we are better equipped to handle. Okay, so the first thing we're going to do is to say, well, I've got the log of this plus the log of that. I can use the second property of logs and write this as the log of a product. The log of x plus 6 times x to the base 3 is equal to 3. Okay? The log of x plus 6 times x would be the log of x plus 6 plus the log of x. Okay. Now I want to make use of the fact that the log of x to the base b is y is equivalent to x equals b to the y power. Okay, the log, in this case is y, is the power that you have to raise the base to get the number. And I'm going to do that over here. In a sense, this is my x, this is my base, this is my y. So I can write this expression, okay, equivalently as, okay, x plus 6 times x is 3 to the 3 power, 3 to the 3rd power. The log of this to the base 3 is 3. That means that 3 is the power that you'd have to raise the base to get x plus 6 times x. Okay, so I use this to go from here to here. This whole mess here, this is like my log of x to the base b is equal to y. That's equivalent to this business here is equal to b to the y. And what comes out of this is a quadratic equation. You can distribute the x. You get x squared plus 6x equals 3 cubed, or 27. X squared plus 6x minus 27 equals 0. This factors rather simply. We're looking for two numbers which multiply to minus 27 and add to 6. We have plus 9 and minus 3. So we have two possible solutions to this problem. X equals minus 9 and x equals 3. Now we look at the numbers, and we see that if we were going to check them in the original problem, we can't use minus 9 because the arguments of our log function have to be positive. We saw that earlier, that if we're taking the log of, say, x to the base b, like this, x has to be positive because it's equivalent to b to the y, and whether y were positive or negative, as long as b is positive, we see that this x is going to come out to be positive. So the problem with minus 9 is when we try to substitute back into the check, we get the log of minus 9 plus 6, the log of minus 3, which we can't do. Here we get the log of minus 9. It's not the negative number so much. For example, if this had been x plus 10, the minus 9 would not upset us. In other words, minus 9 plus 10 would be 1. That would be all right. It's just that when you plug in, you cannot get a negative for the argument. This would, of course, still be upsetting because you'd have the log of minus 9. So that lets the minus 9 out. Now let's look at the 3. We can still check our value in the original equation. And maybe it would be a good exercise to try to do that. Going back to the original equation, log of x plus 6 to the base 3 plus log of x to the base 3 is equal to 3. We'd like to check the value x equals 3. Now, if we let x equal 3, we'd get the log of 3 plus 6, the log of 9 to the base 3, plus the log of 3 to the base 3 should be equal to 3. Now, the log of 9 to the base 3, we're going to have to figure that out. What is the log of 9 to the base 3? And we're going to need the log of 3 to the base 3. Well, I claim that the log of 9 to the base 3 is 2. Because what is this? What are we looking for? We're looking for the power that you'd have to raise the base to get the number. This is true since 3 squared is equal to 9. 2 is the power that you'd have to raise the base to get 9. So therefore, the log of 9 to the base 3 is 2. Similarly, the log of 3 to the base 3 is 1, since 1 is the power that you'd have to raise the base 3 to get the number 3. So knowing that the log of 9 to the base 3 is 2, and the log of 3 to the base 3 is 1, we have, of course, a check. 3 equals 3, and it works out. So the solution to this equation here is x equals 3. And that's the only solution. And that brings us to the end of the table.